So in order to find another thermodynamic property, we will move to chapter 6. Chapter 6, we defined, you remember when we talk about the fundamental property relations, we defined something called Gibbs free energy. And we said one of the fundamental property relations, Gibbs free energy, is calculated by this equation. And according to this equation, Gibbs free energy is function of temperature and pressure. At phase change, or at phase equilibrium, or at phase transition, for pure substance, again, what we are talking about is pure substance, not mixture. For pure substance, phase change occurs at constant pressure, constant temperature. Water, for example, at 1 atmosphere, 100 degrees Celsius, it will change its phase completely from liquid to vapor. So at fixed temperature, at fixed pressure, phase change will occur. So at phase transition, there is no change in temperature, dT is 0. There is no change in pressure, dP is 0. So dP is 0, dt is 0. So at phase conditions, there is no change happening in Gibbs free energy. So this means at phase conditions, the value of Gibbs free energy for the liquid phase equal the value of Gibbs free energy for the vapor phase. Okay? And this is a good sign that we can use Gibbs free energy as a criterion. So this is the second property we start to think of using it. So entropy, we failed of using it because of it's hard to use it. Then we end up with using, or the idea of using Gibbs free energy. Because Gibbs free energy at phase conditions, there's no change happening in Gibbs free energy because it's function of temperature and pressure. Temperature and pressure already constants at phase transition. So this means Gibbs free energy for liquid, Gibbs free energy for vapor, these two phases that changing will have the same value of Gibbs free energy. Okay, how can we relate Gibbs free energy to entropy? As we said, for any process to occur, the entropy is increasing, right? So now for any process to occur, if we will use Gibbs free energy, we need to understand what will be the changes happening to Gibbs free energy. So if I have case 1 and case 2, I have Gibbs free energy for case 1, Gibbs free energy for case 2, how I can design the direction of the process? Am I moving from case 1 to case 2 or case 2 from case 1? I can know this from entropy, similar to what we did here. I just compare the entropy and the process will go in the direction of increasing entropy. So is this the same thing for Gibbs free energy or Gibbs free energy has different approach? To answer this question, we need to recall two chapters, chapter 3 and 5. Chapter 3, we explain the energy equation, that we have the change in internal energy with respect to time. The accumulation is work of expansion contraction plus heat. This is for closed system. Entropy balance, this is the equation of entropy balance. The change of entropy with respect to time is Q over T plus S generation. If we rewrite this equation, we need to put Q like on one side of the equation, on the left side on the equation, and put the temperature on the left side, put generation on the other side. So this will be the equation. Q, the amount of heat added or removed from the system, equal all of this. And now we start to put all of these equations together. So we have du pi dt, or d pi dt mu, is work of expansion contraction, work of expansion contraction plus Q. What is work of expansion contraction? Negative dpv pi dt, the general equation for work of expansion contraction. What is Q? All of this from the entropy equation. So now we have the change in internal energy equal this work of expansion contraction plus this Q. So let's put this equation together again. This is the equation we have. D u pi dt equal work of expansion contraction plus Q. This is work of expansion contraction, and this is Q from the entropy equation. Okay. Here we have d pi dt. Here we have d pi dt. Here we have d pi dt. Combine all of d pi dt terms in one side of the equation. So d pi dt mu plus pv plus tms. And the left side, the only side that doesn't contain d by dt, this is the generation term. So if you can see here, we have mu, this is the internal energy. We have ms, this is s. Okay, so we have this equation we'll have by combining energy balance equation with the entropy equation. If you remember, here we have U plus PV. Anyone remember what is equivalent? Internal energy plus PV? Enthalpy. We have U plus PV. This is equivalent to enthalpy. Then we can see d by dt enthalpy minus Ts. This is equivalent to minus generation. And enthalpy minus Ts, this is nothing but Gibbs free energy. So all of what we did, we used the first law of thermodynamics, energy balance equation, second law of thermodynamics, entropy equation. We combine both of them together in order to end up with an equation that relates Gibbs free energy with the generation of entropy. So the whole idea that we have information about entropy, we can know the direction of the process based on the value of the entropy, but we cannot use entropy as a criterion for phase equilibrium. We can use Gibbs free energy as a criterion, but Gibbs free energy cannot help us to know what is the direction of the process. But if we relate Gibbs free energy to entropy, then we can know this, based on this relationship, we can know the direction of the process. Again, if you recall the equation, so this equation here tells you this Gibbs free energy is only for the system. So again, Gibbs free energy that we have here, this is related for the system, not the surrounding, only the system. And this is the problem we have with entropy. In order to use entropy as a criterion for phase equilibrium, we need to know entropy of system, entropy of surrounding, combine them together to calculate total entropy. But Gibbs free energy for this equation, it's only for the system. So only Gibbs free energy for the system can be used as a criterion for phase equilibrium. And this is a good thing that we can use. So we removed any need to calculate or find any information for the surrounding. We now focus only on the system. And this is one advantage of using Gibbs free energy. We remove any data or any need for calculating any property for the surrounding, and only we can focus on the system. Any process to occur in a spontaneous way, S generation for this process is positive, right? Because the entropy is increasing. Makes sense? So if and temperature, absolute temperature is always positive. And this is multiplies by negative. So this term is negative. So for any process to occur, dg by dt will be positive or negative? Will be negative. Make sense? So this means if you have any process to occur, since the generation of entropy is positive, entropy increasing, then dg by dt of the system will decrease, will be negative. If we get back to this figure we have what I tell, if we have reactant, so this reactant will move from this case to this case. Because this is the case at which it has maximum entropy. If you have product, they will react together in order to go to this case. So always the process is occurring in the direction of increasing entropy. But now since we have negative sign in the equation that relates Gibbs free energy to entropy, this will be the curve that describe whatever happening for any process in terms of Gibbs free energy. If you have reactant, so Gibbs free energy, so the process will occur in the direction of having this case, and this is the equilibrium condition, and this will be minimum Gibbs free energy. If you have a product here, this product will move and settle at this condition. So the relationship or combining first and second law of thermodynamics give us one like indicator that you can know the direction of the process if you know the total entropy change of the system and surrounding, or if you have Gibbs free energy of the system. Total entropy change is increasing, okay, but Gibbs free energy is decrease. So if you have case 1 and I have case 2, and here I have information of system, and for this system I know like entropy of the system S1, entropy of the system S2, and if entropy of the system is more than, like S1 is more than S2, again, this is not enough to know the direction. because for entropy we need to know surrounding. What is S1 for the surrounding? What is S2 for the surrounding? This is here system, and then calculate total. So this is S1 total, and this is S2 total, which is summation of system plus surrounding. If S1 total is more than S2 total, then the process will move in this direction. But for Gibbs-free energy, what you need to have only the system. If you know Gibbs-free energy for the system, and you know Gibbs-free energy for the system at case number 2, and if Gibbs-free energy at case number 2 is more than, like case number 1, so the process will move from higher Gibbs-free energy to lower Gibbs-free energy of the system. Okay, so now we can use Gibbs-free energy to know the direction of the process. It's much simpler because we know only the value of the system, not the total, and because of the negative sign, it's opposite to entropy. Process occur in direction of increasing entropy, process occur in the direction of decreasing Gibbs-free energy. Okay, so let's give a summary of everything we have. So now for phase change, for phase transition, there is no change in Gibbs-free energy. So this means the change of Gibbs-free energy at phase change is 0. Or Gibbs-free energy for the first phase equal Gibbs-free energy for the second phase. For any process to occur spontaneously, the total entropy increases, or Gibbs-free energy of the system, this one decrease. Equilibrium is achieved when they have, or the stable condition achieved when we have the minimum value of Gibbs-free energy, and there's no changing happening in Gibbs-free energy at this condition. Okay, and again, the lower value of Gibbs-free energy, this is the more stable phase. If you have any case and you have lower Gibbs-free energy, then make sure that the process will move to this case, the case of lower Gibbs-free energy, which is corresponding to more entropy. Clear?